Hello, everybody. So it's really great to be back. I guess Hack.lu is one of my favorite conferences ever. I will be talking about Heap exploitation, but don't be really happy about that because it's the not so profitable path towards it. I will be talking mostly about the things that are not working at all. And that's why it makes it really important to tell that this is something that I'm doing in my free time. And by free time, I really mean like after work, weekends, or as some of you know, during flights around the world. And so don't be judgmental. It's really free time stuff. And another thing is I'm not a vulnerability researcher. That means that everything that I'm doing here is like experimental and mostly theoretical, because for those that know me knows that I do a lot of math. So about me, I like binaries. So it doesn't really matter which kind of binaries, as long as they are compiled. And I really like assembly. I work mostly with x86, but I also try to do stuff in MIPS and other kind of stuff. I'm also a core member and board member of Black Hoodie. That's a reverse engineering bootcamp just for women that we organize once in a year, plus some spin-offs like we had this Monday here at Hack.lu. I'm also in the program committee, but I cannot vote for my talk, so don't worry about that. I'm also working for Disobey as a technical lead of content there. I give lots of workshops on assembly, reverse engineering, and other stuff. And I'm trying to get really good at karaoke. So that's the most important thing that you should know about me. I'm terrible, but I'm working on that. So what I'm going to talk about today here is about constraint logic programming, solvers, static analysis, and all the problems that you have with that, about memory, of course, and heap, or kind of. So the first question that I have is always like, SAT, SMT, what are you talking about? So it's just a solver. It's something that it's going to solve our problems. Sounds good, right? And the problem is, solvers are that like the SAT problem is a known theoretical problem. It's an NP complete problem. That means you cannot solve it with algorithms really easily, not in a way that we know how to do it. And everything needs to be written in Boolean functions. And that's pretty complex. So you cannot easily describe the whole word just with logic, right? So that's the reason people are working on SMT solvers. That's like a front end, not like web applications front end, a bit dirtier. But it's still a front end that makes it easier to write real world problems in a way that it's translated to Boolean logic. So how this work is mostly like you have something like this picture, and the solvers are going to try to reason about questions that you make about that. So you have the situation that you are seeing here, and the question is, can I go outside without getting wet? So the solver is going to look at it and it'll see, okay, there is a lot of water on the street. It looks like rain, so, oh, wait, I see people with umbrellas and they are not wet. So it will give, yes, there is a possibility, and this is getting an umbrella. And then you say, no, that is not going to work with me, I don't have an umbrella. What else? And then it will check again and say, yeah, so nope. You don't have a chance to get outside without getting wet. So I'm talking about constraints. And I realized that the easiest way to explain what constraints are is like looking at a maze. The constraints would be like walls inside this maze. So at first you don't have so many walls. So you can find more ways to go from the beginning to the end. And every time that you add a constraint, it's like you are adding a wall in your maze. So it's getting harder and harder, and the paths towards the beginning to the end are less and lesser. And this is a quote that you are always going to see in my talks, because that's the guy that like mostly inspired me to change from other science to computer science, and that's it. He told me that there is something that can solve my problems without me having to do that, so why not? And what I use to solve my problems is something that it's using constraint programming and also solvers. That's the automate theory improvement. So if you want to know how the SMT solver itself works, or like internals of the logic inside, we can talk about that later offline because that's just 45 minutes. But you can assume that's a black box. You put a problem inside of it like we did before with the rain. And if I can get outside and everything, and then the solver will analyze all the constraints that you have of the situation and the limitations, and then it say, is it feasible or not to do what you want? And the good part of it is like, it's not just saying to you, yeah, you can do that, but also how you can achieve with all your constraints to solve your problem the way you want. And why is it interesting is like, people were using it before in the math. The mathematicians wanted to take small little pieces of problems, put them together to solve a bigger one. So you had like these problems that are worth millions on the list, like P equals NP, right? So you can model small parts of this problem, put inside a SMT solver and try to solve and infer that the bigger one is also feasible. Why do we want to do that in computer science? You can think about code verification, right? You have like hardware and software, and you want to verify that it's actually working the way it's supposed to do. So you can have like little asserts, really small pieces of code asserting that it's doing this, right? The things that you want to do, and then you can scale it, and then you have large scale verification. People that are also using SMT solvers in logic for computer science are the Langsec people. They are actually implementing the logic inside the parsers so that the language itself is safe, so you cannot do much wrong if you are using the right parser. And how I use it also, and other people, is for symbolic engines, symbolic execution engines. So symbolic execution is just like exploring the code with symbolic values in that, so you don't have like concrete input, you have like a symbolic input, and you go through the whole code like that. And combined with SMT solvers, like I'm using, and other engines too, it will reason about if a path is doable or not, if I want to explore that path or not, if it makes sense, if it's unreachable anyway, and so on. So it looks like this one. If you look at the code, it's easier to understand, but in a theoretical approach, that I mostly talk about here is you extend the language that you have in your Turing machine with symbolic values, so then you can explore your whole code without using like concrete values. And then you can find bugs in your code without even executing it, without needing to fuzz it, because you have the domains that are possible, and you find something that it's not. A really easy algorithm, like just to get an idea how it works, would be like this. So you create processes every time that you reach a state, and then you have the process number and a state, and you add this process to the domain of your whole system or whole program. And then you just iterate it. Every time that you reach a branching point in your code that it's feasible, you add both of the paths inside your domain. And if it's not, then you just negate the one that it's not possible and put in your domain. And then you continue exploring your code until the end. To understand how I was trying to use this concept for automating the exploitation of heaps, you need to understand how the memory works, because it's a bit different of other stuff. So memory is just there to store information, right? And in the hardware level, it looks really simple. It's just a latch. So you have like and or latches everywhere. And if you just look like that, it's really, really simple. I mean, I'm not an ASCII artist, and I can even make that. So it's not hard. But in your processors, it gets a bit harder because you have more complexity. So you need to imagine that you don't have just one of it, because this one can store just one bit, And if you think about how many bits you have in your SRAM right now, it's a bit more than that. And this one is also independent of the whole context. Right now you have like metrics of this kind of stuff inside of your processor communicating with each other to have like a bunch of information that belongs together. But if the hardware is the same, what's the difference in the memory? And anyway, that we know we have more, right? Yeah, we don't have 50 shades, we have just like 2 or 3, depends who you're talking with, but we are going to talk about the heap, not about the stack. For the stack, we already have like a bunch of work done on automated exploit for stack, but not for the heap. And the funny thing is like, why? I guess you know how the stack looks like. It's mostly like that. It's easy to understand. It's just put stuff together. And then you have the heap that looks like this. So the thing is, if you think about you have a stack of books and you are just taking one from above, it's easy. You know which book to get the next. With the heap, it's completely different. If I say to you, yeah, I want that book, and you have this, it's a mess. So it's pretty hard to find the right position on your memory to actually exploit a heap with underflows or overflows, because you don't even know exactly where it is. And the heap is also a managed memory, so you have regions for everything somewhere. And even in the Intel books, they are defining like that the heap is unspecified place, so you cannot know anyway. So how can I put that all together? Before I used it to, before I was using SMTs over symbolic execution, all these things to make my job easier. That was malware analysis. But that work is done. And I remember that before I used it to say like, I know that people are using it for fuzzing, code verification, binary analysis, and also for POCs and exploit generation, right? And I was like, okay, people are doing it, but why is not going further? What's the problem there? What are people doing wrong? And the thing is, I started to write some simple proof of concepts using all this theoretical approach. And I like it because I see a lot of POCs out there from bugs. And most of the people are publish a POC for something. And then 2 weeks later, or maybe 1 week later, I see a bunch of malware using this same code from GitHub and infecting a lot of machines. And that's not fair, right? It makes my job harder. So what I started to do is like, okay, you can write POCs using logic. So I can infer that the code is broken without actually giving a working code for it. I don't need to exploit it to prove that it's buggy. And then I started, okay, so maybe there's something there. And I started looking for stuff. And I decided to start with code verification, and that's a really broad field. And then I look at like, okay, if I'm looking for all the bugs, it's not really going to work, right? Because I mean, it's my free time. I need to do, I also have a life. As you know, I really want to be a karaoke singer. So, yeah, I know. So I decided to make my problem smaller, like the mathematicians make. So if I cannot prove like everything at once, maybe if I break it into pieces like Jack the Ripper, it will work. So that's what I did. I broke my problems of code verification into smaller pieces. And then I decided to do like, okay, let's just find bugs. But not all the bugs, but the exploitable bugs. Because they have something else. And maybe someone wants to pay for it, because if it's buggy, but no one can exploit it, it's just a bad code, then it's just bad code. But if you can exploit this, then you have a value of it. And it makes more sense to fix something that it's exploitable than to just fix buggy code, right? So my problem was a bit smaller now, but it wasn't enough because I decided to check how to crash a code. And it's easy. you can just write everywhere, and then the memory is corrupted and is crashed, right? But what does that mean? And then I decided, okay, that's not enough. I will make it even smaller. I don't want to just crash something. I want to have control of the code. And then I started to check all the techniques that are already there, the research that have been done. So I saw that people were using exploratory testing for finding the bugs. That's not my field, it's fun. Tried it once, but not mine. I saw people using dynamic tainted analysis. Yeah, more interesting. Still not mine because I cannot really do it good with Prolog. And that's my free time, so I choose what I want to do, right? And then people have like abstract interpretation, and I started to learn about that and read a lot of papers, and it sounds super interesting. So I was like, okay, that could be weekends. And then I saw CLI. That's an open source and symbolic execution engine, whatever. It runs on top at LLVM, super cool. The problem is it's not scalable. You can use like CLI for small pieces of source code, but not for binaries and a lot of other stuff. So I saw Manticore. It's working on binary. It's also a symbolic execution engine. It's also doing tainted analysis. And it has binary instrumentation. The problem is you can use Manticore for crack maze. And you can use Manticore for small binaries. But I don't want to store a bunch of binaries on my computer just to play around on the weekends. So what I'm doing is I'm using just the bin folder of my computer and like poking everywhere. And that doesn't work with Manticore. It crashes all the time. There is also another engine that I found out like last week, so I didn't have time to put everything here, but the name is Manhai. And it's pretty cool, but I didn't test it to the end, so I cannot say much about them, but it sounds interesting. What I choose to do is, like always, it's free time, so I decided to implement my own. And I'm using forward symbolic execution. That's a symbolic execution, but I'm using the SMT solvers in the branching points to decide if it makes sense or not to go to the end. And I try to not have the 100% code covered because my computer cannot do that. So the first thing was find a bug. That was easy. It was really easy. You just need the symbolic execution there, it's filtering the domains, and then you have the bugs. But for that I needed to define, because I like definitions and math, so I defined what does that mean that there is a bug there. So I defined this vulnerable path is this, as you can see. And then I had a plan. But for that, I also need a theorem, right? So I wanted to define what kind of stuff I want to prove in the end of my research. So my idea was that given a program, I can automatically find the vulnerabilities and generate exploits for them. Sounds normal, sounds okay. Yeah. And then I started to check which kind of vulnerabilities I'm looking for. The thing is, I also needed to define a really small scope for it, because you cannot check everything. The second problem was that you have a lot of techniques to finding bugs, but not for the checking if the exploit works. So I started like, okay, I will check for direct influence of the user. Every time that a user has the power of giving some kind of input and this input is changing the control flow of the program, that's direct influence. So it's like when you define malloc with a size, you are defining directly something in the control flow of your program, right? And then you have the indirect. That is something like that, where the user has the power of changing something, but not directly. So if you want to change something there, you need to know how your input is influencing the whole code in a way that it makes sense to exploit it. So the second step was to check if the vulnerability that we found in the first one is exploitable, because I didn't want to find all of them, just the one that makes sense, right? And for that I was thinking, okay, let's use concretization, but that wasn't that easy anymore. Because then I had like this huge amount of possible inputs that you have in your domains. And if you put all of them and test all of them, then it's just fuzzing it. That's not really automating the way I was thinking about. And I needed a definition, so there it is. I wanted to find the paths that are vulnerable, and at the same time, with the same input, you need to find a function that it makes it exploitable. And both of them need to be true. If one of them are not true, that's not what I'm looking for. I hope that's clear. The third step was implement the function that makes both sides true. Yeah. And then I implemented something. The problem was that it was working just for a real special case. So it was not generic enough, in my opinion. So it was working for some kind of malloc. Like, I had a code for each kind of bug code class. So I had like a piece of a function that was working just for free, right after free. And then I had one that it was just working for underflows. And that's just working for a special case, not always. And then I noticed that it's just working most of the time. It's not every time. Why? If the bug is the same, right? And I'm there. And even doing it manually was still not working all the times. And then I was thinking, okay, if this is the case, is it really automation? If not even like doing by hand is working anymore. So I added an extra step that was the evaluation of the whole project. And then all the problems that I had along the way. The first one was like finding the heap. That was a challenge by itself. I am really happy that I had people talking to me and explaining to me and writing amazing papers. I'm going to list them in the end. That's a real complex problem, how to find the heap in the memory itself. And then the exploit verification. As I told you before, you have like this huge amount of possible inputs that makes you more fuzz the code than a really automated exploit. And then you had the third one. That's the state-space explosion. I don't know if you know, but I'm doing everything on this small thing here. It doesn't work like that. You are doing like a symbolic execution. You have like a huge amount of memory being used all the time. And then I had the problem with environmental definition, and that is what I didn't expect. And I guess it's a flaw because I am not a vulnerability researcher, so I was not thinking about that. But every time when I was checking, the first time my memory was clean because it was just booting my computer. The second time I was doing again, and I had something in my memory already. And then the third time I was just overwriting my memory. And every time that I was running the code without rebooting it, I had stuff there. So you really need to define which kind of environment you are using before starting in the first place. So the limitations that I had are the first one, they are always the same when talking about symbolic execution and code verification or any kind of binary analysis. It's basically the halting problem. Because if you have a code to verify another code, it's theoretically impossible to assume that every time that you are verifying a program with another program that it will hold for the property that you are testing for. So that means that you cannot write a code to verify another code and be sure that you can do that every single time. And the second one is that if you define that your program doesn't depend on the user input, you are still inside the decidable languages. The problem was that when I was executing the code multiple times in my memory and had like garbage still on my memory, I run into the undecidable languages. And if I don't take care of it, I can even go further to the non-Turing acceptable languages because there are states in my memory that I don't want to go there, but we are talking about quantum physics. I cannot know what is inside every single thing on my processor, right? It's impossible to know the state of it. And then we have the practical thing. We are still running normal processors. They are not quantum computers right now. So the problem is that the normal processors that everyone has everywhere in the phones, in the computer, or whatever, they are finite state machines. That means they are Turing machines, and they are decidable. So I cannot write a code that is running in another bubble, in the undecidable languages, in a decidable product, because that's incompatible, right? So after all this theoretical approach that I had, my first idea was that I could do something like, okay, symbolic execution is super cool for vulnerability research, right? But then I needed to change. That can be. And I really believe that it can be. Because the models are still pretty hard to write and define and everything. So the main takeaway for myself was that I need to understand better how vulnerability research works. Because what I did before were mostly related to my job, so I knew how things work manually, so I could automate it faster, right? If you know how to do it yourself, you see the patterns, you know how it works, you can automate. And I'm pretty sure that if a vulnerability research sit in front of the code and define the models, it would work way better and way faster than it worked for me. That's the reason that right now I decided to write a kind of assistant to write the constraints for security problems that are going into the SMT solver. So instead of modeling just for malware and then modeling it just for heap exploitation and then modeling it again for stack overflows or whatever, what I can do is just create a framework that will assist security researchers that have the knowledge already from the other side, like I had from the malware side, to write these models by themselves and then just use the engine in the backend. Because they don't need to know how SMT solvers work, but they know how to model things in a way that it's logical to check. And the people that I wanted to thank about all this research it's like my last at least 8 months, are Sean and Marion. Sean published a paper, it's already published, it's not anymore to appear, about heap layout manipulation. So he was kind of solving the problem that I had about finding the heap. And it was really inspiring to talk with him, like he was helping me all the time. And every time that I thought about like giving up because it wasn't working the way I was thinking it was supposed to work, he would just say, no, you are in a good path, just keep doing it. And Marion, because she was the one that first showed me binaries. Another paper that helped me a lot was the models that Vannegar presented in the Landsec conference. He was modeling the heap for the first time in a theoretical approach that I could use to model the exploits after. The Intel documentation kind of helped, but not really. It depends the way you look at it. And that's it.